Good evening, all of you. Is my voice clear to all? And the video also? Say, is it clear? So today I have a sore throat, so please adjust with my voice. Thank you for the consideration. So we start the new topic that finite fields. So with regard to UPSC point of view, this topic also contains a variety of questions and problems also, which will be interesting for you. So in this context, we mainly learn the word that what is meant by extension of a field. What is meant by extension of a field? So in the number system, we know that Q, R, C, these are the fields. Q is a subset of R is a subset of C. In other words, we can say that Q is a subfield of R and R is a subfield of C. Agree all of you? Yes or no? So we say that R is an extension of Q and C is an extension of R. So whenever we know a field and its subfield, the field is called an extension of the subfield. And one other property is the field acts as a vector space over the subfield. So, you know what is meant by a vector space while dealing with the concept of linear algebra. We learned about what is a vector space and what is meant by a dimension and what is meant by a basis. Do you know the concepts or not? Vector space, basis and dimension. Tell me. If you have forgotten, then I will retell the definition again. What is meant by a vector space? Please specify. So can you recollect the definition of vector space or not? Hello? Can you recollect the definition of vector space? Right? So, if you take the concept of vector space, this also we call it as a linear space. You take a set V, the elements in it are called vectors. And we take a field F. And elements in the field are called scalars. V is called vector space over F if it satisfies the conditions that these are the four properties in relation to V comma plus abelian group satisfied by the vector space. So usually the elements in the set V are called vectors, whatever may be the elements in V. Basically we take a field, it may be a rational number system or real number system or complex number system. F is a field. The element in the fields are called scalars. The numbers we call with the other name that scalars. And the set V is called a vector space over F if it satisfies the following properties, where alpha comma beta are vectors taken in V, A comma B are numbers called as scalars taken in F. This is the definition of vector space. Similarly, we say that from this definition, R over Q is a vector space, C over R is a vector space, because these sets satisfy the properties what I have mentioned here with respect to the definition of a vector space. Okay? Are you clear? So, while taking the context of vector space, we deal with two more things, that we have a word basis, we have a word dimension, right? So let us retake the definitions one more time, then we can understand this concept of extension in a clear way. Suppose you take a vector space V of F. In this vector space, we consider a subset. So S is a subset of V containing all non-zero vectors. We say that this subset is a basis of V if it satisfies two conditions. The first condition is S is linearly independent set. Second one is S spans V. So whenever S satisfies these two conditions, we say that S is a basis of V. Here we need to understand that a vector space may have so many bases. If you want to say that a non-empty set is a basis, it must satisfy the two conditions. And coming to the word dimension, so the number of elements in the basis. In any basis, particularly we say, is called dimension. The number of elements in any basis is called dimension. So let me say, if I have taken a set S with the values alpha 1, alpha 2, so on alpha 10, and this set is satisfying the two conditions, then we say that S is a basis of V and dimension of V is equal to 10, because S contains exactly 10 elements. So please take a note of this definition. After noting, please inform. Any questions for anybody over this definition? Say yes or no. Right. Now, so coming to the concept of finite extensions, I mean the extensions again, whenever you take the fields of the order, say A is a subset of B and B is a subset of C, then we say that C is extension of B and B is extension of A. So we can say that C is vector space over B and B is vector space over A. And I know that what is the meaning of spanning? The formal definition is known to all of you. Am I correct? The definition of spanning. Tell me. Can you recollect? Can I mention that one more time? So here spanning is nothing but, since we have taken that C is extension of B and B is extension of A, in C you can find a set of values. This is a basis for C. So from this very context we can say that if you take any value in C, say X belongs to C, you can write this X as a combination of the basis elements, where, let me say, if the basis contains the values alpha 1 so on alpha 10, let us take for convenience, then you can write X is equal to A1 alpha 1 plus A2 alpha 2 plus so on plus A10 alpha 10. So where the numbers A1, A2, so on A10 are taken in the field, since C is the vector space over B, these scalars A1, A2, so on A10 will belong to B. In other words, the value X is written as number into vector plus number into vector plus so on plus number into vector. This is the actual context here. So if you say that the basis contains 10 elements, then mathematically we denote that C over B is equal to 10. It means that B is a subfield of C. In other words, C is extension of B. We can find a basis for C such that which contains 10 elements. Okay. So C may contain so many elements. These 10 elements will generate C. So in particular, we can say that what are the values are B, it is okay. Apart from this, you can have 10 additional elements in C, which will generate the whole set C. That is the idea behind it. Clear? Are you clear or not? Sorry. Now let us take a small example that. So let us take the value root 2. It is a number. Now, for convenience, say alpha is equal to root 2. Squaring on both sides, alpha square equal to 2. This implies alpha square minus 2 equal to 0. So in other words, alpha satisfies the equation x square minus 2 equal to 0. Alpha satisfies the equation x square minus 2 equal to 0. Accepted? Now, let us verify that is this polynomial irreducible over Q or not. So here we can apply the Einstein criterion. So if you write this in the form of a polynomial, it is nothing but minus 2 plus 0 into x plus 1 into x square. By taking the prime number, p is equal to 2. P divides the constant, p divides x coefficient, p does not divide the leading coefficient, and p square does not divide the constant term. Accepted? Therefore, we can have a prime number which satisfies Einstein criteria for x square minus 2 equal to 0. Hence, this polynomial is irreducible over Q. Now, what happens if you consider this value exclusively on Q? So, I will take a new set Q of root 2. So, don't misunderstand that as you have taken Z of root 2 earlier, that set is different, this set is different. Don't compare these two. So, apart from the rational numbers, it is containing one more value, that is root 2. So, this Q of root 2 is a field. So, what will be the hierarchy here? This is Q, this is Q of root 2. So, Q is subfield of Q of root 2. Hence, we say that this Q of root 2 is an extension of Q. The additional element what we have taken here, this element we call it as algebraic over Q. So what is meant by algebraic? Whenever you take a value, say alpha, we say that alpha is algebraic over a particular field if you are able to find an irreducible polynomial of smallest degree such that alpha is root of that polynomial. Then this is called as an algebraic element over the set. Here in this example, root 2 is a value and root 2 is algebraic over Q because root 2 satisfies the polynomial x square minus 2 equal to 0, and this is the smallest degree polynomial, and this is the irreducible polynomial. So we should have an irreducible polynomial where the coefficients are exclusively taken in Q. The polynomial what you are taking must belong to the field. The coefficients must belong to the field, and you should have a root for that polynomial, and the polynomial must be irreducible. This is the basic criteria to say that an element is algebraic over a field F. Okay? Clear for all? Now you can say one more thing. This kind of elements are so many. You can take q of root 2. You can take q of root 3, q of root 5. Suppose I have taken another set that so here I have taken only one value in addition, I mean extra. Here I have taken two values extra when compared to q. So this is extension of q and this is extension of q of root 2. Automatically this will become the extension of q. Are you clear? What I mentioned? Now, if you calculate the vector space, here it contains two values. Here it contains two values. In other words, it has a basis having one value, say root 2. So if you calculate the dimension, you are going to take the dimension by means of the polynomial satisfied by it. So whenever you have a vector space, whenever you have an extension, you need to calculate what is the dimension for it. So we specify the dimension by means of the irreducible polynomial satisfied by it. So the importance of polynomial here is, if you want to know the dimension of q of root 2 over q, it is nothing but the degree of the polynomial satisfied by root 2. So here it is x square minus 2, as the dimension is nothing but 2. Are you clear now? How we are specifying the dimension in the context of extension. So I am saying that this is vector space over Q. Accepted? So for every vector space, we can find a basis for it. If you know what are the number of elements in it, then the number of elements in the basis is called dimension. So if you want to find the dimension of this set, q of root 2 over q, it is nothing but the degree of the polynomial satisfied by this root 2. Here, root 2 satisfies the polynomial x square minus 2. Its degree is 2, hence the dimension is 2. That is what I am saying. Clear to all? Now there are some standard results based on this context. How do we find a basis? How to calculate the irreducible polynomials? These things we need to know. I want to take some sample problems as well as results on that. So give me a moment, I will take some problems for you. So in this context, we will take one more definition. What is meant by a minimal polynomial? Exactly. 1 and root 2 are elements of the basis here. Actually, while determining the basis, we will have a formula. Let me say, so if you have a formula, if you have a polynomial, say degree is n, and this polynomial has root alpha. So how to determine the basis? The basis is nothing but 1 alpha, alpha square, so on alpha power n minus 1. This is the basis. So the importance of degree is, if you know that the degree is n, in other words, alpha satisfies a polynomial of degree n, then this is the respective basis with respect to the vector space. You please take a note of this. This is useful while solving many problems. Okay? Are you clear? Now, let us take that. You take the value root 2 plus 5. Now, what is the minimal polynomial over Q for this element? What is the minimal polynomial for this element over Q? So, do you know the meaning of monic irreducible polynomial? Yes or no? You know the definition of irreducible polynomial, right? What is meant by irreducible polynomial? Right. So monic means the leading coefficient must be 1. Let me say, so let us take that this is irreducible polynomial. This is also irreducible polynomial. Here the coefficient is 2, so this is not monic. Here the coefficient is 1, so this is monic. Okay. So we have to take an irreducible polynomial in which leading coefficient must be 1. That polynomial is called monic, and a monic irreducible polynomial is called minimal polynomial. So coming to the question part, if I have taken root 2 plus 5, what is the minimal polynomial for this value? It is simple math calculation. Let us do that. So let us take this is equal to alpha. So implies you can say that alpha minus 5 is equal to root 2. Now let us take squaring on both sides. From this you can say alpha square plus 25 minus 10 alpha is equal to 2. Implies that alpha square minus 10 alpha plus 23 equal to 0. You accepted? So this is the monic irreducible polynomial because alpha is satisfying the polynomial x square minus 10x plus 23 equal to 0. This is the monic irreducible polynomial. And here a question comes, how do we say that it is irreducible? Isn't it? So apart from Einstein criterion, you can use the other technique that you need to say a polynomial is irreducible or reducible by means of root. If a polynomial has rational root, it is reducible over Q. If the polynomial has irrational root, it is irreducible over Q. So here root 2 plus 5 is an irrational number. Accepted? And from this very context, immediately we say that this value is root of this polynomial. So this polynomial has irrational root, not a rational root. Therefore, this is irreducible over Q. Clear? If you have noted, let me take one more. Now take another one that say it is also an easy one. Let us take the other thing. So take root of -1 plus root 2. Let us take this one. So if we have taken that this is equal to alpha, squaring on both sides, you will get alpha square is equal to -1 plus root 2, implies alpha square plus 1 is equal to root 2. Again, squaring on both sides, you will have alpha power 4 plus 2 alpha plus 1 is equal to 2, implies alpha power 4 plus 2 alpha minus 1 equal to 0. Accepted? I mean, this is 2 alpha square, say. Accepted? Yes or no? So, this is the irreducible polynomial satisfied by alpha. X power 4 plus 2x square minus 1 equal to 0. Square minus 1 equal. So in this way, we calculate the polynomials, the monic irreducible polynomials. Now, based on this, we will do a small problem which is useful to calculate the field extensions. Now, you consider the field q of root 2 comma root 5. So, it is our claim that find a value a such that q of root 2 comma root 5 is equal to q of a. Okay, this is the question part. So the underlined idea here is, if you observe that this is a field which is having two values, root 2, root 5, other than q. Accepted? So this set contains the values generated by root 2, root 5 apart from q. So our intention is, can we find a set apart from having two elements, a single element is sufficient such that these two are equal. So the values generated by these two elements are simply generated by only one element a. Is it possible to find such element or not? That was the question part. Clear? Are you clear with the context or not? Now, for this kind of problems, simply the answer is, you add the two values. So our value a is nothing but root 2 plus root 5. For this, specifically there is a theorem. How can we confirm that the sum of the two values is equivalent to the generating sets of these two? that is at present immaterial. We don't require to prove the result. So my intention is I want to show that q of root 2 comma root 5 is equal to q of root 2 plus root 5. This is my claim actually. Okay. So my intention is this is subset of this and this is subset of this, that I want to prove actually. So in the first place, this set contains two values, to root 5. So as you are dealing with a field, the vector space itself, by applying the closure property, addition of the two values also belong to the set. So root 2 plus root 5 will belong to this set. Therefore we can say that the values generated by this set also belong to this. Hence we can say q of root 2 plus root 5 is a subset of q of root 2 comma root 5. Do you accept it? Or and of root 2 root 5 is a subset of this one. So let us go for that one. Now if you consider the set q of root 2 plus root 5, the special element in this set is root 2 plus root 5. Since it is a field, every field will possess the inverse. The inverse of this also belong to the same set. So I can say the reciprocal root 2 plus root 5 belong to the set. So if you rationalize this, root 2 minus root 5 by minus 3. So after doing rationalization for this value belongs to this. Please understand that this is nothing but accepted or not. So here this is by default a value in Q. As you were saying that the product belongs to this set, from the properties of vector spaces, immediately you can say that this value also belongs to this set. Therefore, root 2 minus root 5 belong to this set. Now, the set what we have considered contains two values. Root 2 plus root 5 is one value. Root 2 minus root 5 is another value. Accept it all? So whenever you have the values there, you can perform addition as well as subtraction. If you add the two values, you will get 2 root 2 belongs to q of root 2 plus root 5. From this you can say that root 2 belongs to q of root 2 plus root 5. Because by default this is a value, hence obviously should belong to this. Similarly, if you subtract these two, you can say that root 5 also belongs to q of root 2 plus root 5. Since these two individual values are belonging to this set, immediately you can say that this is subset of q of root 2 plus root 5. So from 1 and 2 we can say that these two are equal. This problem is important because based on this, we will do calculating the dimension of a vector space on a set. So please take a note of that. If you have any other queries, you can ask. After noting, please tell. Right? Now, the result what we are going to prove is please take a note of this result. After noting, please tell. So K is a finite extension of L. L is a finite extension of F. Then K is a finite extension of F, and K over F is equal to K over L into L over F. That was the question tag. Okay. Are you clear? Now, for our understanding, let us take the hierarchy that what is meant by finite extension. So it means that L is a subfield of K. If you calculate a basis for K, then it contains a finite number of values. Okay. The same definition is applicable for L is finite extension of F. In other words, we can say that we can calculate a basis for K such that K contains a finite number of values. So, if you say that as we have a vector space K over L, it will contain a basis, so it has a dimension. Let us take a value that this is M. It means that in the field K, you can have M values which are basis for K. So let us take the values as alpha 1, alpha 2, so on, alpha m, it is a basis of K. Similarly, L is a vector space over F. So L also have the dimension. So let us take that the dimension is n. It means that we can find a basis for L having n elements. So you take the values as beta 1, beta 2, so on, beta n. This is a basis of L over F. So technically speaking, as per the problem considered, what is the dimension of K over F? From the very diagram, we can understand that this is the product of these two, M, N. Nothing but K over L into L over F. Accepted? So theoretically, we have to prove that. The underlined idea here is, since we are calculating a basis, we need to construct a set having mn elements. So we have to construct a set having mn elements such that which is a basis of K over F. So we need to identify what is the set having mn elements, that is one. And secondly, that set must be a basis. It means that it must be linearly independent and it must span the vector space K. Okay? That we have to prove theoretically. Now, any guesses for anybody how to construct a set having mn elements there? Anybody has any idea over that? Please tell. Yes or no? It is very simple. Since we need to get mn values, here we have the set having m elements, here we have the set having n elements. If you consider the product, it is having mn elements. So it is nothing but I take the set alpha I, beta j, where 1 less than or equal to I less than or equal to m, 1 less than or equal to j less than or equal to n. So this set contains mn elements and I am going to prove that it is a basis of K over F. In other words, I simply multiplying the basis elements here with the basis elements of the other set. That is actually I am doing. Okay? Did you get the idea? Now, first of all, we have to show that this is a spanning set for K over F, that is 1, and this is linearly independent. So what is meant by linearly independent? If you write a linear combination with these values, the scalars in that must be 0 always. So if you consider the linear combination that so this is a linear combination where the result is 0, where A, I, J are scalars taken in F. Are you clear? Now this thing I can write it as So you can understand that if you feel that this is a number, summation number into beta, it is of the form. So it is nothing but the linear combination of betas. So for your understanding, I will write a small thing that is useful for you to understand the sigma notation here. So let me say I have taken a set x1, x2, so on, xn. If you want to write the linear combination, it is nothing but a1 x1 plus so on plus an xn. This thing we write it as summation I is equal to 1 to n ai xi, where these xi are nothing but the vectors and these values are nothing but the numbers taken in the field. Clear? Similarly, aij are the scalars taken in the field, and this is a vector, this is a vector, having two summations, because I am considering alphas as well as betas at a time. I am considering the product of the values, right? So you have to write the two summations. Clear? So basing on betas, since we have a summation here, this is a linear combination of betas like this. Since betas are linearly independent as they are basis, the scalars here must be 0. Therefore, summation j is equal to 1 to n aij alpha is equal to 0. Again, this is a linear combination of alphas. Since alphas are basis, they are linearly independent. The scalars in the linear combination must be 0. So this is nothing but all aij is equal to 0. So here I have considered the linear combination in which all the scalars have become 0. Therefore, this set is linearly independent. If you understand the context of linear independence in vector space, if you have studied earlier in the class sessions, then it is very easy to understand from this point of view. Or if you are hearing for the first time, then you get a confusion. So if anybody has any doubt what is meant by linear combination and linear independent, I will give a small hint that, let me say, if you have taken a set of vectors, so you write a linear combination. What is meant by linear combination here? You are multiplying the vector with a number, the scalar, and you sum up all the values. So sum of the product of scalar and vector you are taking. Whenever the result is equal to 0, then all the coefficients a1, a2, so on, an, whatever the scalars you are taking, it must be equal to 0. If that is the only possibility, then we say that this set is linearly independent. If sum of these values is equal to 0, but some scalars a1, a2, an are non-zero, then this set is called linearly dependent. That was the underlined idea. So let me say in a small notation, I have taken x1 is equal to 1, 0, 0, x2 is equal to 0, 1, 0, x3 is equal to 0, 0, 1. So what is meant by linear combination here? a1 into 1, 0, 0 plus b1 into 0, 1, 0 plus c1 into 0, 0, 1. And I am saying that if you simplify the entire thing, you will get a 0 vector. Now, what is the possibility for a1, b1, c1? Can you substitute any non-zero numbers such that on summing all these values, you will get 0, 0, 0? If you get non-zero values in place of a1, b1, c1, the set is linearly dependent. If the only possibility is if you take a as 0, b as 0 and c as 0, that means all the scalars are 0, then only it is becoming equal to 0. Then we say that the set is linearly independent. Okay? Can you recollect the definition one more time? So here we say that the set 1 0 0 0 1 0 0 0 1 is a basis for the three-dimensional space. If you consider x, y, z, 1 0 0 0 1 0 0 0 1 is a basis for R cube, the three-dimensional space. Why? Because if you take any 3D vector, that can be written as a combination of these three values. Suppose I have taken the vector 2 3 4. So this 2 3 4 can be written as 2 into 1 0 0 plus 3 into 0 0 0 1 0 plus 4 into 0 0 1. So this thing is written as a combination of the values. This kind of problems we have solved in vector spaces earlier. And we know that this set is linearly independent. Unless you substitute 0 0 0 here, you cannot get that output as 0 vector. So here also, whenever you say that this is a basis, this is a basis, these are basically linearly independent. So this is a combination of betas. Since betas are linearly independent, the scalar part here must be 0. Therefore, this must be 0. Again, it is looking as a linear combination of alphas. Since alphas are linearly independent, the scalar part must be here 0. So these things must be 0. Clear? So in this understanding, we say that this set is linearly independent. Okay, all? Are you getting the idea or not? So if you have studied vector spaces earlier, I mean linear algebra part earlier in the class sessions, it is easy. Otherwise you get confused. What is this actually? Fine. So this is the proof of linear independence. Will everyone agree for this or not? Right. Now, we have to prove that the set alpha I beta j spans the set K. So what is meant by spanning here? If you take any value in K, it should be written like a linear combination of alpha I into beta j. That we are going to prove. So let us take that X is an element in K. Now what happens? K is a vector space over L. So, and I have taken that for K over L, there is a basis. This is the basis for K over L. And this is a basis for L over F. So from the very definition of basis, if you take any value in K, that can be written as a linear combination of these values, and the scalars are taken in the field. And what is the field here? The field is L. So you can write X is equal to the linear combination of C1 alpha 1 plus C2 alpha 2 plus so on plus Cm alpha m, where the scalars are taken in the field E. Because alphas are basis for K over L. Again, since you are taking that C1, C2, so on, Cm are elements in the, are elements in L. Since L is a vector space over F, whatever the value you take here, that can be written as a linear combination of basis. And what is the basis of L over F? It is nothing but beta 1, beta 2, so on, beta n. It means that you can write C1 as a linear combination of D1 beta 1 plus so on plus Dn beta n. If you take C2, C2 can be written as a linear combination of so on betas. Similarly, everything. So C1 is written as linear combination using betas. C2 is written as linear combination of using betas. So on. Cm is written as linear combination using betas. So therefore, you can say that each Ca can be replaced with the combination of betas. Hence, you can say that you can write this value as summation I is equal to 1 to m, summation j is equal to 1 to n, dij alpha I beta j. So each C is a linear combination of betas. So D11, D12, D13, that is why I am taking for C1. So the portion we need to understand is C1 is taken as D11 beta 1 plus D12 beta 2 plus so on plus D1n beta n. If you take the second value C2, D21 beta 1 plus D22 beta 2 plus so on plus D2n beta n. Like this, each C is written as a linear combination of betas. So in a general notation, all these C's are written like this. Because this is nothing but summation I is equal to 1 to m Ci alpha I. So each Ci is written like this. So this is the final linear combination. Okay. So please take a note of this. So in this way, it spans K. Therefore, the result gets completed.